we actually ordered a king oyster mushroom kit from Amazon and started to...
And there are all kinds of problems with the king oyster mushrooms. They've escaped and are now kind of taking over in the wild.
Oh, I did not know that.
Competing, yes.
Oh, really? Oh, okay.
So you may be part of this problem.
I'm sure that happened before we did that.
We
follow all appropriate protocols.
Welcome back to Research Matters, where we explore how Cornell researchers are solving real-world problems in surprising and inspiring ways. I'm your host, Laura Riley. Today we're diving into robotics, not the kind made of bolts and steel. My guest is Professor Robert Shepard, Director of Graduate Studies for Mechanical Engineering, and the John F. Carr Professor of Mechanical Engineering. He designs robots made of living tissues, fungal networks, squishy materials, and even structures printed all at once in 3D space. He's showing us what happens when machines stop trying to imitate life and actually start partnering with it. Rob, thanks so much for being here.
Thanks for having me.
All right, so I want to start with the class that you teach. We just saw what was in his book bag, and it was an awful lot of, let's just say it was a Catholic small c array of reading material. But what is this class that you teach that you just finished?
It's a mechanical engineering class co-instructed with systems engineering, and it's the framework for how to invent new products that people want. And the books I showed you were more about the influences I had and draw from and invention in my research, but also that I try to apply to my course.
So is it an entrepreneurship class, or is it more kind of an esoteric, theoretical, the origin of invention?
It's more theoretical with a framework and tools you can actually use, but I wouldn't say it's an entrepreneurship class. We do delve deeply into patents and how and look at how invention progresses over time. Before this started, you were mentioning aluminum cans, and one of the lectures is about how aluminum cans proliferated and why they didn't exist in mass 100 years ago and why they're used a lot today, as an example.
Oh, that's fascinating. Yeah, no, that's great. So do you, for the students in this class, is there an invention component to it? Do they have to invent something, or at least kind of contemplate what they would invent?
Just a small task of having to invent something.
Yeah. Easy.
So my co-instructor, Sirietta Simoncini from Systems Engineering, she takes the students through an empathy fieldwork process where they try to identify sometimes outlandish behavior and figure out why it exists, if it's useful, and then how we can adopt it and make it something that's serviceable to more people.
Mm-hmm. Fascinating. All right. So I have read a bunch of stories in the Cornell Chronicle about your work. And to me, they always seem kind of phantasmagorical. You know, I read the recent one on kind of fungal networks and robotics. I think there was one, I'm not sure if it was in the Cornell Chronicle, but it was about robots that have little explosions that advance their movement. So where should we start with the work that maybe we'll start more recent work and then work our way backwards? So,
okay. Those sound like very different things, but they were arrived at using the same process. Our group, we try to think of future needs for robotics and then find the fundamental principles required to enable it, whether it sounds strange or not. If it sounds strange, it's even better because there'll be less people working on it. And so the explosions came first. That came from wanting to have something high power, but small. Batteries.
How small are we talking? What's the
3 millimeter diameter discs that can actuate to similar 3 millimeter heights, but using 10 newtons, like 10 apples kind of forces.
Okay.
So a lot of power, small area. Batteries don't work well for that. The smaller you make a battery, it's mostly packaging and not much energy or power delivery. So at that point, we thought, what other power sources can we use? We're not going to use a nuclear power source or little black holes. So chemical fuels.
Solar seems bad. Wind, also very bad in this case.
Yeah, it doesn't scale well very small. But of course, at large scale, those are great solutions. But chemical fuels have a lot of energy in a small volume. So that's where we went through there. And then we made little insect scale robots that could very high power motions. And then aggregates of these actuators to make braille displays that are full-scale braille displays that don't require being plugged in, and it solves a big problem in the blind community.
Okay, wait, go back to that.
Mm-hmm.
So braille. So you're saying these are tactile. These are things that a visually impaired person can feel.
Mm-hmm.
How does it change the braille experience?
Well, it's very difficult for and I should say the first author in this paper was Ronald Heiser, a fantastic student of mine, is now at MIT. He wanted to demonstrate this capability in Braille. Mm-hmm. And so he did an I-Core experience with that was enabled by Cornell as well. So we got to talk. He went to a conference for the blind. He met Stevie Wonder, all these kinds of things.
Wow.
Yeah.
That right there is worth the price of admission, for sure.
He loved that part. I would have too. And the thing is, the blind have a difficult time with devices that allow them to read music or do math, things that aren't line by line kind of things. Mm-hmm. And so a full...
Because it's 6 dots, right? 6 dots in different...
Yes.
Okay.
Yes, that's right. Well, you know a lot. And
that
I knew very little.
That exhausts my Braille knowledge.
You used phantasmagoric earlier. I'm still going to look that up. But so but this Braille display issue is one that's a problem when we want something portable. Mm-hmm. Getting the number of dots in the way Braille displays work now would create a very huge, heavy thing, and where most of it would just be, a little bit of area you can read. So this solution allowed us to make forceful tactile inputs in small areas without creating a huge, bulky, expensive, heavy display.
Mm-hmm. I can totally see the utility of that. So something I've read in your work is the word biohybrid robot appears a lot. Like what is that? What does that mean?
That's where you use living tissue to augment your robot to provide new capabilities. And biology is really good at self-assembly. Like it starts with amino acids and creates proteins, and proteins assemble into other functions that we see and express at macro scale, into if you're a human or mammal or something like that. And we just can't do that artificially. We can't start... And
self-repair too, right? I mean, isn't that like a thing that
yes,
living
absolutely.
tissue is good at?
Yes, that's right. Yeah. And there's a lot of work. We've got work on self-healing chemistry, which is synthetic too. But yeah, living tissues will heal themselves. Mm-hmm. Mammal tissue is really good at high force density. It can create a lot of force in a small volume, and you can grow it in weird architectures and things like that. But mammal tissue is sensitive, and it's a very arduous process to culture it and get it to work appropriately. Actually, funnily enough, Ronald is also working on mammalian tissue biohybrids in his postdoc. But what I wanted to do was work on biohybrid systems without the difficulty of mammalian culture. Okay. So we actually ordered a king oyster mushroom kit from Amazon and started to...
And there are all kinds of problems with the king oyster mushrooms. They've escaped and are now kind of taking over in the wild.
Oh, I did not know that.
Competing, yes.
Oh, really? Oh, okay.
So you may be part of this problem.
I'm sure that happened before we did that.
Takeover.
We follow all appropriate protocols.
So anyway, all right. So the oyster mushroom kits, which are common now on Amazon.
So we ordered it, and the problem with culturing mushrooms is not them dying. It's making sure other mushrooms or other fungus don't grow in the same petri dish. Mm-hmm. But that's the only issue we had. And once they're grown, they're stable for months. Unlike mammal tissue, if you brought it outside and just put it in contact with the air, it would die almost immediately. Anyway, so that means that allows us to put the mushroom mycelium, which is the sort of, you can think of it as a root network.
It's the underground. So the mushroom's up here and the mycelium is under.
Right, yes.
So you're working with the mycelial part of the oyster mushroom. Right. Why is that a good product for your work? Because
the fruiting body, which is what most people think of as the mushroom, is temporary. Mm-hmm. Like it grows and spores and dies and goes away. The mycelium is persistent. So we wanted to keep that in contact with we use electrodes to interpret the signal and control a robot. And so you can make sheets of it. Right now, I'm working with a Larissa Shepard in human ecology who's spinning fibrous mats, and we're culturing these spores into like sheets of mycelia that you can wrap around robots for wide area perception. And I think
so I know these sheets are being used for packaging and a whole bunch of other things right now, and even for, fake bacon and all that kind of thing. But so these mycelial sheets basically, do they live in perpetuity, or like what's the lifespan of one of these kind of things?
Yeah, a big difference between which the work Ecovocative does, which you were mentioning, is really great. The difference is theirs is not alive, and ours is alive, in how we're using it. And so it lives for months, but then it actually does start to die as it can't grow anymore in the volume it's in. It starts to die. And then we notice the signals decaying in our robots. And it's a very interesting problem to solve, to how to deal with controlling a robot with degrading signals, and then even thinking about how to rejuvenate it afterwards. It's a whole different problem space. And by working on mycelia instead of mammalian tissue, we can start to address it now in real systems rather than wait another 20, 30 years for these mammalian-based biohybrid robots to be stable in the wild.
Okay, so how do you convey what you want the mycelium to signal to the robot?
Yeah.
Like how do you program the mushroom, essentially?
Yeah, that's a really great question. We aren't programming the mushroom. We're listening to what it's saying and telling the robot to do what we want based on the information the mycelium perceives. And I intentionally use the word perceive instead of sense, because the mycelium is taking environmental inputs, multiple inputs, and encoding it into voltages that we're reading. It's making sense of the environment, and we are taking that signal and trying to do something with it. An example is, so mycelium mushroom, the fungal kingdom, is, and if a mycologist is hearing this, I'm sure they're gritting their teeth. But as an engineer, the fungal species kingdom is similar to mammal.
Yeah. It's the largest organism, right?
It's a large organism. We use antibiotics from them because they don't like bacteria either, and obviously the bad kind. But and so if to be simple, a mushroom doesn't like the environment it's in, we may not like it either. And so if we can understand the action potential, the voltages and electrical signals coming from these mycelia as good or bad, then our robots can make a decision about searching the space for something that's maybe harmful to us. So it would be going against what the mycelium favors. But,
so it favors as in the way a plant leans towards the sun, or
yes,
or the way
yes,
I don't know, muscle will kind of avoid. I mean, it doesn't have a brain per se, right? But it'll avoid adverse perception or conditions.
So heliotropism, like plants trying to follow the sun, and maybe a more complex reflex action where we blink when something goes in our eye. We're more thinking of the mycelium as helping us understand if the environment is bad or good. And in the case of, let's say, a nuclear reactor meltdown, we could send a fleet of these biohybrid robots into it, and then they could quickly assess the largest areas of concentration of radiation, for example.
Sure. Yeah. Well, I was kind of thinking about kind of all of this is so cool, but what are the practical applications for some of this? I mean, I can imagine kind of self-healing tissues being advantageous in a robot if it were in space or deep underwater or in some place where fixing it for humans would be difficult.
Yes.
Like, what are the kinds of questions that you're asking right now? What problems are you trying to solve?
Well, you kind of nailed it there. The robots we make we don't shy away from complexity, which is one of the things that differentiates us. Our group, I think that in order to have robots that are autonomous, agile, and capable of operating untethered for long periods of time, have to be complicated. An integrated network of multiple systems, some amount of redundancy and things like that. And so these are four unmanned missions to Mars, things like that. And if something breaks, it does need to heal. And so we approach that from artificially, but also with living tissues like you're describing now too.
Wow, that is wonderful. I know that you've done a lot of work in kind of, volumetric 3D printing as well. And how does that fit in with your robotics work?
Well, as I said, it's a good connection because the robots we make are complicated. There's a lot of multifunctional integrated components, kind of like organ systems. To assemble that is hard to do. And the reason we're using living tissue is because they build from the nanoscale up to the macro scale. We can't do that, but we can kind of get there from printing, where you start from the bottom and grow out. And and get complexity at the same time. And it's the same amount of time to print a brick as it is to print a replica of La Sagrada Familia or something like that. So,
okay. Although I'd like to see the latter, that'd be great.
It's wonderful. The best thing I've ever seen in my life. So then we can get complex things and co-integrated systems at time scales of a graduate student.
Mm-hmm. Yeah. Actually, Gaudi is like a really good 3D printing kind of environment. Yeah.
Yeah, absolutely.
Yeah,
I think about it all the time.
Yeah, that could be wonderful. You could redo all of the wonderful places in Barcelona with. Yeah. All right. So in terms of the 3D printing, what specific things are you working on? What are the specific kind of thorny questions that you're trying to overcome?
The most recent challenge in what's called volumetric additive manufacturing. It's not a layer by layer process. Everything solidifies all at once, like a Star Trek replicator. And in that case, the issue is it's small. Like we're talking cubic centimeter volumes. And the problem that the community had primarily was thinking about absorption of light. It's a photopolymerization process where light has to penetrate through the volume. But actually, we discovered that a bigger challenge initially is that when you do the chemistry, it creates heat, and then that heat moves the liquid around that you're trying to solidify all at once and makes it impossible to make the thing. So we invented an active cooling technique that allows you to print large things in the same amount of time.
So the cooling, is this about kind of structural integrity, or what does the cooling allow you to do?
Well, we actually, in this case, we don't want anything to move when it's being printed. We want the liquid or solid to allow light to pass through it, but everything stays in the same place. When you create heat, if it's a liquid, you cause motion, convective flow, that then makes it so you can't solidify the object where you want it to. So by cooling it, we remove the heat so we don't get these flows, and then we can make the object solid there. Mm-hmm.
So this process, as opposed to the layering,
yes.
What bottlenecks or what problems does that potentially solve for industry or for, scaling robotics?
We think a lot. In fact, we started a company a year ago trying to commercialize this. One is because the material doesn't have to move, you have a lot more options of materials. Mm-hmm. So you can use more viscous materials.
Like what would be one of these viscous materials?
Polyurethane that has an oligomer, like a precursor that's longer.
Okay.
And so when it's longer, these chains are harder to move around. They're thicker, like oil in your car, but even thicker than that, even more viscous than that. So, and then you have to somehow transport it in most other material system. But in ours, it just sits there. It doesn't matter how viscous it is. It could even be a solid, and you could do that. And with that, you can have tougher rubbers, for example, or tougher plastics, these kinds of things. So if you were to try to print a shoe, this way, you could print it out of materials that are even better than what shoes are made out of now. Mm-hmm. Whereas other kinds of printing technology, you could print a shoe, but it's going to be worse materials than now and also take a longer time. Or the feet of robots.
The feet of robots, yeah. The shoes of robots.
Yes. Maybe shoes. That's great. We got it. That'll work.
All right. So I know that some of the work that you've done has had direct applications for agriculture.
Mm-hmm. Yes.
And in my life, I've done a lot of stories on the adoption of robotics, like the slow and maybe overly optimistic adoption of robotics in the field, because obviously labor for agriculture is the big
one of them.
headache,
Mm-hmm.
for all kinds of reasons. So what kinds of things would your array of robotics allow to happen in the field?
Great question, I think, because it's our main. So we want to make robots that are agile. They can perform dexterous movements, manipulate objects that are in an intricate way, but also do that for a long period of time. Mm-hmm. A lot of people in the robotics community are doing great work solving the dexterity agility problem. Tons of money going into robot hands, humanoid hands, things like that.
That don't like ruin the fruit, but
Yeah.
pick it at maximum ripeness.
Yeah.
Yeah.
But if you try to do that for long period, if you try to deploy a humanoid robot in the field to pick fruit, it's going to be able to do it for like 45 minutes.
And then what happens?
And then it has to go recharge.
Okay, so that's worse than a lot of F2A visa workers, right? Yeah.
Yeah. So we need to. So we're imagining this challenge is going to be solved. Robots are going to be agile and all this other stuff. But after that, then what? Efficiency matters. Energy storage matters.
Yeah.
How long can they do this for? And so those are things we're trying to solve by making multifunctional use of energy, where parts of the machine not only are the frame or the actuators, but they're also the energy storage. So 90% of the weight is also a battery.
Yeah.
Well, it's a lot like how humans work, especially me.
Yeah, I hadn't thought about that as is even harder than those kind of, the grabber, making the grabbers better.
Yeah.
How is
I don't know if
how's it
it's
gonna
harder. It's just, it's something that isn't being addressed right now. And we want it to have that solution ready for when the rest of the problems are solved.
Okay.
Yeah.
So agriculturally, are there crops or are there situations where this would be especially useful?
Mm-hmm.
I mean, I imagine corn and soy is already pretty automated.
Mm-hmm.
So are we talking about specialty crops or tree fruit or what are the things that in the next 5 years will pivot to robotic, planting, harvesting?
You're right. The current row crops are designed for the equipment we have now. Mm-hmm. There's a lot of nutrient-rich produce that isn't appropriate for that isn't being farmed at scale. There's also the opportunity to mix crops together not in rows, and ways that have some that allow reduced pesticide use and better use of nutrients.
Kind of more biodynamic
Right.
planting strategies.
Yes.
or
some that are resistant to certain insects that shield the other ones. But that's a very complicated process. But if you have robotics that are adaptive and can work in these systems, then you can maybe do that. And then we'd have more nutrient-dense food with less agricultural waste.
So is that predicated on kind of use of GPS coupled with AI? I imagine you have to have a robot that can identify, this thing will be ripe tomorrow that I've just passed over. I have to remember precisely where it is. Is that right? Or is it that kind of thing?
That's certainly a lot of the story. But there's also, my favorite fruit is the pawpaw.
You're the only one.
You've never had it?
I have had a pawpaw.
Oh, they're delicious.
Yeah. I think they grow in Florida sometimes,
They grow
right?
here.
Oh, do they really?
They grow here in Michigan.
Is there a pawpaw festival or something?
I don't know, but I know that I'm not going to give away my hidden grove.
Okay. All right. No. You don't have to do anything.
Actually, you know what? I will. The Macadam Nut Farm, or Nut Grove, there's a bunch of pawpaw trees.
Okay.
And anyway, you can go there and pick them. They're only ripe for a short period of time. Mm-hmm. They taste like mango banana custard.
Yeah.
But
you never see them in stores, and that's because they're so ephemeral, right?
Exactly. Yes, that's right. They don't transport well. They don't have a long ripening period, and you can't
you didn't think this conversation was going today. The pawpaw.
I'm very passionate about these things. And you can't see that they're ripe. You have to feel that they're ripe. So vision and GPS is only part of the story. Being able to feel it and get through occlusions like leaves that are blocking things and stuff like that. It's also a big part of the story.
Wow. Mm-hmm. We're almost out of time, but one more kind of agricultural question. Mm-hmm. I imagine robots, kind of a phalanx of guardian robots, could ward off pests or large scale, blights or is that another arena that this could be brought to bear on?
I've seen some efforts in weeding robots and probably insect hunting robots. But I think I prefer the mixed breed plant where we integrate plants that are resistant to some of these things or fight them in their own way. Like plants, they practice chemical warfare like nobody's business.
Yeah.
I mean, so I think there's probably a way to use plants to do it. But maybe robots could maybe do that. It'd be a very energy intense way to do it.
All right. So all of this is so fascinating to me that we could go on and on. But I do want to ask, like, is there any kind of what's the next big question on your horizon, or the next big problem you're aiming to solve?
Well, it is the use of the biohybrid mycelium-based robots for threat detection, radiological, chemical, that thing, and how we can coordinate swarms of robots to localize the origins of these threats.
Well, Rob, thank you so much for coming in today and for showing us how robotics is reshaping what machines can do and how they can help us in fields from farming to medicine to space exploration. If you want to learn more about Rob Shepard's lab, look up the Organic Robotics Lab at Cornell Engineering. And if you enjoyed this conversation, remember that Research Matters brings you stories just like this. Research that doesn't stay in the lab, but reaches into the real world to solve real-world problems. To watch more episodes or to learn about the breakthroughs happening across Cornell, visit our website or subscribe wherever you get your podcasts. I'm Laura Riley. Thanks for joining us.